We are talking about continuous functions. That's what we started talking about last time, and that's what the homework is about. So check it out. I said last time I want to talk about two theorems concerning continuous functions, about combining continuous functions together. The first one was simpler. That's just that you can compose two continuous functions, and the composition, G composed with F, will be a continuous function. The other thing I want to talk about for continuous functions, combining them together, is more complicated, and it's called what the book calls the patching lemma. So this is patching continuous functions. And the picture that you should have in mind is if I have so a picture of like two real functions being patched together is something like if I have one function like that. Now I'm going to imagine these are functions, their domains are not all of R. I mean, you can do it with all of R, but it's not an interesting picture. But the idea is you have two functions with different domains, and they agree on the part where the domains overlap. So maybe the other function is like this. So this is, I will call the red one F and the blue one G. And their domains, I will call A and B in the theorem. So A is this domain. In the x-axis, it's the domain of the red function F. And the domain of the G function is, this one here, like that, right? And that I will call B. And the theorem basically says if F and G are equal on A intersect B, that is where the two domains overlap, the two functions have to actually match in their values on that overlap, which they do in my picture. If they are equal on the intersection, then F and G can be pasted together to make a continuous function on the union, A union B, right? If each of them individually is continuous and they agree on the intersection, you can sort of glue the two functions together, and it makes a big continuous function on A union B, all right? And in fact, we can write down what that function would be. This is sort of the kind of thing that annoys calculus students, but the way that you would write this is it's f of x if x is in A, and it's g of x if x is in B, right? That's how you would write the definition of the big function that you get after patching them together. It's in two pieces, right? Now these two pieces have some overlap to them, but it's sometimes it's equal to f of x and sometimes it's equal to g of x. And in the overlap, it's equal to both because they are equal on the overlap. All right. This is the idea behind the patching lemma. Or is it the pasting lemma? It's the pasting lemma. Sorry, I said patching. This is not as far as I know, this is not like a well-known word for it. This is just what our book calls it. The pasting lemma. Patching is just as good, isn't it? However you prefer. All right. So this is the picture. There is a technicality about this, as there often are. The overlap actually cannot just be any set. The set on which they overlap, it turns out, must be a closed set. Actually, the individual sets A and B have to both be closed sets in order for this to work. If one of them is not closed, you can get something weird like, let me just say, A and B must be closed in order for this to work. For example, if A and B are not closed, you can do something weird like if A was, say, this domain here without that point, so this, letting A be this is not closed. And then let's say B is this domain here, which does include that point, but I mean, B can be closed actually. The fact is, both of them have to be closed. In this example, one is closed, but the other is not. And now, actually, you can draw a function on A, a continuous function on A, and also a continuous function on B, but they can't be patched together. Something like, here's Here's my F, which does not include that point. And then my G actually doesn't even have to match because this is the G, this is the F. All right. And these can't be patched or pasted, whatever you want to say. All right. You might say, well, that's because they don't agree on the overlap. But actually, there is no overlap in this case. The overlap is the empty set. And so they don't have to agree anywhere. And they don't agree anywhere. And you can't paste them together into a continuous function. That's the point. You might say, well, can I just like move this one up there? And then you can glue them together. Yeah, but that would be a different function. So the theorem is going to say, if f and g are any continuous function, and they agree on the overlap, then you can paste them together to make a continuous function. These two functions cannot be pasted together. The moral of the story, or the fact, is that if this only will work, it's only guaranteed to work if A and B are both closed sets. Yeah.
What if we move B more to the left?
Yeah, in this case, if we move B more to the left to make it so that they do overlap on some points, then this example, this is sort of a counterexample to the pasting if one of the sets is not closed. If you do that, it's no longer a counterexample. But this counterexample is enough to demonstrate that something goes wrong if one of the sets is not closed. All right. Okay, anyway, let's try to actually write the theorem and do a proof of it, because it does involve some amount of details. The business about A and B being closed sets is a technicality that is necessary in order to make it all work. So let's see if we can. I will write this down as a theorem. This is called the pasting lemma. And here's to write it out formally. So I say if f, I'm on the wrong page here. Sorry. Can I start differently? I want to say let x and y be topological spaces. And I let x equal A union B. So x is the domain of both of them together after you paste them together. So let x be A union B, where A and B are both closed. This is necessary in order for the theorem to work properly. A and B are both closed. And then we have two continuous functions. So f has domain A. G has domain B. These are both continuous. And they have to agree on the overlap. So I say f of x equal g of x for all x in A intersect B. That says they agree on the overlapping part. That's all the setup. Then the conclusion of the theorem says you can make that pasted together one. So I'm going to say h of x equals, this is the pasted version, f of x if x is in A, g of x if x is in B, is continuous. That's the whole point of the theorem. You can paste them together into this function h, and that function is continuous. All right. So this is the long statement of the theorem. And this really is the whole part that we have to prove. Just the fact that when you paste it together, it ends up being continuous. All right. You can see my little counterexample here. Yeah, technically you can paste together f and g. It's just that it won't be a continuous function. It'll be a function with this kind of jump in it. All right. We need to demonstrate that when you paste it together like this, the result will be continuous. All right. Let's see if we can do it. I hope everybody remembers the definition of continuous. Anyone want to refresh my memory? I know at least one of you does, because I was just talking to one of you about it, but I don't have that one I've already heard knows about it. Can anyone refresh our memory? Don't say epsilon. Yeah?
If u is inverse image of U is open.
Yes, she said if U is an open set, then the inverse image of U is open. So the standard proof that something is continuous always begins by saying let U be an open set. Then I'm going to show that H is the function I'm talking about here. Then I'm going to show that H inverse of U is also an open set. Now, that was a little misdirection, actually. We are not going to do the proof like that. There's a fact that I mentioned last time that the definition of continuity works just as well if you use the word closed instead of open. And this is something that you're going to do on the homework. So I'm going to say it turns out the closed version is more convenient than the open version in this particular scenario. So we're going to use the closed version of continuity. So that means f is continuous when U closed implies f inverse of U is closed. As I said last time, this is equivalent. You can do, when you're talking about continuous functions, you can define it in terms of open sets. You can also define it in terms of closed sets, and you get the same concept. And when you're proving something is continuous, I mean, usually you use open sets, but sometimes, if you want to, you can try to do it in terms of closed sets. It turns out in this particular scenario, the closed version works a little bit better. So the structure of the proof is going to say let U be closed in Y, right? Y is the codomain. And then I have to we'll show that H inverse of U is closed in X. All right. Okay, let's do it. So these, actually, I'm sorry, I keep on misdirecting. I meant to, rather than U, I'm going to call it C, just so that we remember that it's closed. Sorry about that. People like to use U for an open set, and it's a little weird to use U for a closed set, so I'm going to call it C. All right, this is what we got to do. So the first thing to realize, and there are a couple of non-obvious steps in this. The first of the slightly non-obvious steps is you have to rewrite, just sort of say, what is H inverse of C? I'm going to say, note that H inverse of C, when you pull the set back through H, think about the way that this function H looks. I'm going to scroll away from here for a moment. Back to this picture is what you should have in your mind. H, on the picture here, H is the entire function all the way from one side to the other. It's the pasted together version. Now, what do you get if you start with a set in the codomain and pull it back using H? Well, remember our set U, or C rather, in this case, looks like a closed set over here, right? And then you're looking for what are all the X values down here, which end up as Y values in this set. And the fact is, some of them end up in this set because of G, and some of them end up in this set because of F, all right? And so when you pull it back, actually, it's the same as, it ends up being like a union of the ones that you pulled back through F and then also the ones that you pulled back through G. Now there's some that are in both, but it doesn't matter. When you're writing it as a union, some can be in both. So this is the first step is, this is actually F inverse of C union G inverse of C. All right. When you pull the points back through the pasted version of the function, or the patched version, there's some of those points which went through F and some of those points which went through G. And so when you pull back H, it's the same as the union of the pullback of F union with the pullback of G. All right? That's really the only hard step. Once you get there, now you can more or less go sort of on autopilot in terms of what you already know and what you see here. Now, we know, in terms of what we already know, we know that F and G are each continuous. and also that A and B are closed sets. Now, the fact that A and B are closed sets has nothing to do with this. Can you say anything, the fact that F and G are both continuous? I'm going to say, since F is continuous, can you say something about F inverse of C? That's the only part of this which has anything to do with F. Yeah? It is closed, yeah, because C is closed. And continuous means if you have a closed and you pull it back, you get a closed. And same with open. So since F is continuous, maybe I'll just say, since F is continuous and C is closed, F inverse of C is closed. I should say specifically closed in A, right? A is the domain of F. So when you pull it back into the domain of F, it's closed in A. All right, and then similarly for G, also since G is continuous and C is closed, G inverse of C is closed in B. All right. Of course, what I mean by that is it's closed in the subspace topology from A or from B, depending on if you're talking about F or G. All right. F inverse of C is closed in A. G inverse of C is closed in B. Remember, A is a subset of X, is the big domain, right? Can we write out what that means? This is just a little blast from the past, I guess, about the subspace topology. Closed in the subspace topology, remember, it means it is the intersection. It is closed in A, means it's a closed set intersected with A, right? That's what the subspace topology means. So F inverse of C is closed in A means F inverse of C is the intersection of some, maybe I'll say D intersected with A for D closed in X. All right? That's what the subspace topology means. It's the intersection of a closed set. Yep.
What did we say it was, the subspace topology?
Well, yeah, this is kind of implied when I say X is A union B, and A and B are both closed. When I'm talking about this, I said this is continuous. That means there's a topology on Y and there is also a topology on A. What is the topology? I guess I didn't say it, but because A is a subset of X, you sort of assume that A uses the subspace topology from X. Yeah. So yeah, to be more technical, you should, if you want to indicate that, you would say it right at this point. Let these be continuous with respect to the subspace topology on A and B. Which I agree. I didn't say that, although that would be understood. If I didn't say anything else, like you wouldn't assume any other topology on A and B. That's the only one to use, unless you have some reason to use some different one. Yeah, that's a good question. Thank you for that. All right, anyway, this is closed in A means that this is true. Okay, I'm going to write the same thing for G. G inverse of C is closed in B means G inverse of C is some other set. I guess I'll just use a big E. Not A, B here. For E closed in X. All right. Just using the definitions. And actually now this is pretty much enough to end the proof. So if you recall, what I started with is this thing, H inverse of C. It is this union, but since then we have realized those things equal this. So to recap, I can say H inverse of C is, okay, F inverse, I'm just going to plug in. F inverse of C is D intersect A. So right here it'll say D intersect A, and then union E intersect B, right? And we want to show that this is closed in X. What are the various sets in there? Well, actually all of those sets. D, this is closed in X, because I just said so. D is closed in X right here. A, is that open or closed? It is closed because we said so at the very beginning of the theorem. This is where we use the fact that A is closed. This step will only work if A is closed. So this is also closed in X. And then E is also closed. Actually, all of these things are closed in X, right? Some of them because we figured it out right here. And the other, so D and E is because of this stuff. A and B is because that was an original hypothesis in the theorem. So this is also closed in X. And so this whole thing will be closed. Because what it is the, first of all, you take this intersection will be closed because the intersection of closed sets is closed. This intersection will also be closed, and then you take the union, and it's also true that the union of closed sets is closed. All right? And that's the end. So this is H inverse of C is closed since it's a union and intersection of closed sets. Only finitely many. Weird things can happen if you if you intersect infinitely many closed sets. It can be non-closed, but if you take a intersection, this is just like 4 sets. So it's no funny business is going to happen when you do the intersections and the unions. All right. And this is the end of the proof. That's what we had to show, right? H inverse is closed. A little hard to hold the whole thing in your mind at once, maybe, but I thought it was a good, a nice little refresh your memory kind of exercise. We're using the subspace topology and also just basic facts about continuous functions. Anybody got any thoughts and prayers about this one? Oh, all right, great. This was the last of the theorems about continuous functions that I wanted to talk about. So I think we can move on to the next section. The next, it's the next section in the book. This was all about continuous functions. As I said last time, maybe, or the time before, I don't know. One of the major reasons for talking about functions at all is that using functions is the proper way to say what it means that 2 topological spaces are the same. Just like in group theory, you use isomorphisms, which are functions, to say that 2 groups are the same. In topology, you use functions if you want to demonstrate that 2 topological spaces are the same. And it's not called an isomorphism in topology. The term for those nice functions, it's called a homeomorphism. Homeomorphisms. In group theory, there's something called the homomorphism without the E. This is homeomorphism. It's different. I don't know why. I don't know what the E means. Homomorphism and homeomorphism, they both mean sort of, morphism is like a function or a transformation or something like that, and homo or homeo, I guess, means like the same. So it's saying this is a transformation between 2 things which are actually the same. That's the idea. So this is what it's called in topology. It is a homeomorphism. And just like an isomorphism in group theory, it basically is a nice function which is also a bijection. It has to be a bijection in order to be a homeomorphism. But this is, let me just say, this is the basic idea of 2 topological spaces being quote unquote the same topologically, as far as what we care about in topology. When I say 2 topological things are actually the same, probably what I mean is they are homeomorphic, or there is a homeomorphism from one to another. And the way that we think about this in topology is X and Y are sort of the same. Expressing this as a function, in terms of functions, X and Y are the same when there exists some function, X to Y, such that, first of all, actually 3 properties are necessary. First of all, F is a bijection. And also f is continuous. Certainly, when we think about two sets being the same, topologically speaking, really what we mean is like you can sort of stretch one around somehow and get the other one. You're not allowed to rip it in half or something like that. That's why this function has to be continuous. All right. And also bijection, I hope everybody remembers. A bijection means one-to-one and onto. Some language that is sometimes used for those things is that it is injective and surjective. Injective means one-to-one. Surjective means onto. I will probably usually say one-to-one and onto. All right. If you want to show something as a bijection, you show that it's one-to-one and onto. Can I tell you a little story about this? This is for some reason, this story from my past has stuck in my mind for a long time. This happened to me when I was in college. I did like a summer research project with one of my math professors over the summer, which some of you have done. And part of this summer thing is we went to a conference together, and it was me and one other student. We went to a conference in Brazil, and we met a bunch of random people at this conference. That there was like an excursion day where we went to see some waterfall in the jungle, and we all got on a bus and went to this thing. And the other student was a nice young woman who, shall I just say, she was much more attractive than me, and there were some certain people at the conference were keen on sitting next to her on the bus and such. It was nothing inappropriate, but she was getting more attention than I was. Anyway, on the bus ride, this guy was sort of chatting with her, and he was like he was a professor somewhere, but still fairly young. And he said one thing that I just overheard him say to her was, he said, like when I want to show something's a bijection, I just show that it's one-to-one, and then I show that it's onto. And I thought that was, like now looking back at that, I think that's kind of ridiculous. But at the time I was like, oh yeah, this guy is really onto something. Like he understands mathematics and women in a way that I can only dream of. Yeah. I never met that guy again at another conference. But anyway, if you are trying to pick up the ladies in the club or something, or the fellas, maybe they're into that too. I thought maybe this is like maybe that's not how everybody does it. No, that is how everybody does it. If you want to show something as a bijection, you show that it's one-to-one, and you also show that it's onto. That's the traditional way. Also, you could just show that it has an inverse. This is another way to do it. Although that like if you're talking about ordinary functions that you can write an equation for, usually it's easy to find the inverse using the equations. But otherwise, you got to show it's one-to-one and onto. And it has to be continuous. Okay, actually, there is a third necessary property, which I'm going to fill in the blanks. I would like to show an example where being a bijection and also continuous actually is not good enough to be a function which is between two sets that are the same. So these two sets, x and y, bijection and continuous is not quite good enough. Bijection and continuous is not enough. For example, if I have, say, my x, this is slightly weird, although we have talked about doing basically this example in the past. If I have my x is a half open interval, and my function f wraps the interval around the circle and makes a circle out of it, all right? We've talked about this, but not with a half open interval. Usually, we talked about this in the context of a quotient function, which would glue together the two endpoints. Now, you could still do that same function here, and actually you don't need both of the endpoints if you intend to glue them together. So this is the same function as that, only this point gets glued here, and it doesn't actually join up with any other point. It just sort of fits in where the other point should have been. All right. But anyway, this f. This is continuous because when you do this like wrapping around the circle, it does not involve ripping any bits, there's no cutting or tearing involved, right? It's only kind of a gluing, even though you're not actually gluing 2 points together. This is continuous, and it's also bijective. Right? The example we talked about before was not a bijection because we glued 2 points together to the same point. But actually, this is not 2 points. There's only 1 point from that to begin with. And so when you glue it together, actually, it is still 1-to-1. That's the concern that you should have. But it is still 1-to-1 because that point is missing here. All right? But that does not count as a homeomorphism because these two things are not topologically the same. The circle really is different from the interval with 1 point removed. All right, so this is continuous and bijective, but not a homeomorphism because we don't want to consider this x and y as being topologically the same. They're not. The circle is different from the interval with 1 point, with one endpoint. All right, what's the problem here? One way to think about this is, it is true that f, when I go sort of from left to right, there's no cutting or tearing necessary to do that function. But if you try to go the other way, like it's a bijection, right? So you should also be thinking about f inverse. If you go the other way, actually you do have to cut it in order to go the other way, all right? So in this particular example, f is continuous, but going back the other way is not continuous because it involves taking this point and separating it from the nearby points down here. All right, so the third condition which is necessary is f inverse is continuous. And here I really mean f inverse as an inverse function because we already said that f is a bijection. That means there is really an inverse function, f inverse. I don't mean like the pullback of a set. I mean it really is a function, and the inverse has to be continuous. All right, you need the ordinary function itself and also the inverse to be continuous. If those things are true, then it means actually that x and y are the same topologically. So let me just write this as a real definition here. I'm going to say a function f going x to y is a homeomorphism if f is a bijection, that is 1-to-1 and onto. Also, f is continuous. And finally, f inverse is continuous. That is a homeomorphism. And in that case, like if there really is a homeomorphism from x to y, in this case, we say x and y are homeomorphic. Homeomorphic, all right? Just like you can say two groups are isomorphic, it means they're the same. Two topological spaces are homeomorphic. It means they are the same topologically speaking, all right? Or actually our book, for whatever reason, our book they don't like to use this word, homeomorphic, although that's usually, like if I'm talking to somebody on the bus about this, that's the word that I would use typically. That's just my own cultural upbringing, I guess. The book more often says topologically equivalent. So topologically equivalent means homeomorphic. It means there is a homeomorphism from one to the other. All right. So let's talk about some simple examples. These are functions which are continuous and bijections, and the inverse is also continuous. How about, so I got simple examples. And actually, for these simple examples, we're actually going to write some formulas of functions, which ordinarily we don't usually write formulas for things in this class, but I'm trying to talk about simple examples. How about this? F of x equals 3x plus 4. Is it a homeomorphism or not? This, of course, is a function R to R, right? The domain is all real numbers, and the codomain also. It's all real numbers. This one is a homeomorphism. First of all, it is continuous. I hope you remember your basic calculus. This is continuous. It's a polynomial, so it's automatically continuous. What about Is it a bijection? It is. Can anyone say, why would you say it's a bijection? That means it's one-to-one and onto. One way to, I mean, you could, I don't know what you were expecting me to say. You could just look at a graph of this, which looks something like that, right? Steeper than that, maybe. Is that one-to-one and onto? I say yes, it's one-to-one, basically because it has like a horizontal line test, right? That indicates that it's one-to-one. There's no two y values that are matching up. And it's onto means that the codomain is actually all of R. You can get every real number out of this. It is one-to-one and onto. Actually, the sort of cuter way to demonstrate that would be you can find a formula for the inverse function. If you remember some obscure tricks from calculus. This is a homeomorphism. So if I were, in this particular case, if I were trying to show this as a bijection, rather than arguing through one-to-one and onto separately, I would just say it's a bijection because there's an inverse. It has an inverse function. And how would I find the inverse function? I would sort of write it like y equals 3x plus 4, and then solve that for x instead of y. This becomes x equals something like y minus 4 over 3. I think I did that right. And so that's the inverse function. So f inverse of x is x minus 4 over 3, right? I hope you probably learned how to do that in middle school or high school or something like that. All right, so that's the inverse. That means it's a bijection if there is an inverse, and this inverse is always defined, right? You might worry about if this inverse has some points where it's undefined, then maybe it's not a true inverse, but it is a true inverse. Is this also continuous? Yeah, this is also a polynomial. You could divide through by the 3 and write it so that it looks like a polynomial. So I will say both f and f inverse are continuous. So it's a homeomorphism. I will often just write homeo. I did it at the top too. Is a homeo. All right, this is not a terribly interesting example. Usually in topology, you talk about a homeomorphism so that you can say the two sets are the same topologically. But the two sets in this case here, f as a function goes R to R. So what we've demonstrated is R is the same as R, which is not really a very interesting fact. But there is a homeomorphism R to R. So R is homeomorphic to R, which is, I already knew that, but this is a simple example, not terribly interesting. All right. What about, here's a slightly more interesting example. Actually, it turns out any two open intervals are homeomorphic. This is something that you probably feel like ought to be true, but for example, the interval 0 to 1 is homeomorphic to the interval 0 to 4. That is to say, in topology, those are the same thing. Now, in geometry, they're not, because the first one is shorter than the second one, right? So they are not the same set geometrically speaking, but topologically speaking, we consider them to be the same set. Can we say, if I call this one x and this one y, can we demonstrate, if you want to show that these are homeomorphic, you have to invent a function from x to y. So we need to create, some function f goes x to y, which is a bijection and continuous, and the inverse is continuous. Anyone want to say? Can you give me a formula? The idea is the domain is some number between 0 and 1. You do something to it, and out you get a number from 0 to 4. It's not a very complicated formula to use. You got an idea?
Like
4x, she says. Yeah, this is how I would do. If I want to start with a number between 0 and 1, and you want to basically like stretch it out to become a number between 0 and 4. F of x equals 4x. Yeah. It takes a number between 0 and 1, and it gives you a number between 0 and 4. If I were to draw the graph of this function, now I am only considering the numbers from 0 to 1 in the domain, and only the numbers from 0 to 4 in the codomain. So really the graph looks like that. Just that. All right? I guess I didn't draw the two axes to scale. Anyway, is this a bijection? And is it continuous? And is the inverse continuous? This is what we have to think about. I mean, just looking at the picture, I think you can tell the answer to all of those questions is yes. But if I wanted to demonstrate it's a bijection, the easiest way to do that, if possible, would be to write down the inverse. Can someone say, what's the inverse? Somebody shout it out. F is you multiply by 4. How do you like think about undo that? Yeah, you divide by 4. So this would be x divided by 4 or 1/4 x, however you like. And both of those are continuous, right? Because they are. They're both polynomials. They are both continuous. All right, so in topology, the moral of the story, any two open intervals are topologically equivalent to one another, which I think you already knew, or at least had that notion already. You can stretch stuff out in topology and it doesn't matter. All right. That I said for two open intervals. Would you believe me if I said the same is true for two closed intervals? Yes, I hope you would. I mean, actually, you would use exactly the same function. It's just when you draw the picture, you would fill in the dots instead. But everything else is all still everything. All the details work the same way. So, can I just say any? So the upshot here is any two open intervals are, I'll use the book's language, topologically equivalent. Also, any two closed intervals are topologically equivalent. All right. What about half open intervals, one with one endpoint versus the other? I think, again, the same thing will be true. If I take one of these intervals, which includes, say, includes the 0, and the other one includes the 0, then still the same function will suffice. So also, any, can I say, intervals which include their lower endpoint, like A, B, and another one, say C, comma, D, these will be topologically equivalent. All right. If you have two intervals which only include the left endpoint, then I mean the same kind of function can be used to make them topologically equivalent. What about? How about something like this versus this, an interval which includes its upper endpoint? Could those be equivalent to one another, or are they different? In R, of course, I mean in R with the standard topology, is a lower endpoint interval equivalent to an upper endpoint? For example, like just as a specific case, this versus the other way, right? Is there a homeomorphism? So if the answer is yes, what you have to do is just tell me a function which takes that thing to that thing. That's a bijection, and inverse and the original function are both continuous. If the answer is no, you don't think that they are homeomorphic, then you have to somehow prove that there can be no such function, and that's typically much harder to do. because you have to consider all possible functions and somehow show that they can't be continuous or bijections or whatever. Anybody have a thought about this? Can you, so you could think about on a picture, you know, one of them looks like this and the other one looks like this. Can you imagine a continuous function which takes that and turns it into that? Does that seem possible, or? You could imagine if you could hold this thing in real life and you're allowed to pick it up and stretch it or whatever. You cannot break it in half. You can't like cut it and reattach it somewhere. Could you actually turn this thing into that thing? Yeah? How would you do it in real life?
Flip it.
Turn it over, yeah. There should be a function that just turns it over. Like that actually is allowed for a continuous function. Can we have a function which turns this interval over? So I'm going to use, anyone have an idea? She said just flip it. This maybe is not easy to just think up out of nowhere. It turns out this will work. 1 minus x is not a complicated function. But if you plug 0 into that, you get 1. If you plug 1 into that, you get 0. And if you plug something in between, say 1/2, here f of 1/2 equals 1/2. That's the point right in the middle, stays where it is. A point closer to the 0 will end up closer to the 1, and so on. All right. So actually this and that, of course, is this is a bijection and also continuous. What's the inverse of that? Actually, the same function is its own inverse, because it would just flip it over again, would get you back to where you started. So this is a bijection. And f and f inverse are continuous. All right. Okay, so our sort of conclusion as far as this little classification here. All different open intervals are equivalent to one another. All different closed intervals are equivalent to one another. And all different sort of half open, half closed intervals are equivalent to one another. Whether it's on the left side or the right side, it doesn't matter. They are all equivalent to one another. So any half open intervals will be homeomorphic. All right. All of this is about sort of finite intervals. That is to say, intervals which don't go out to infinity. If it goes out to infinity, then maybe maybe the situation is a little bit different. So, and maybe we'll let's talk about that next time. What about, you know, something like a to infinity, or a to infinity like that, or I mean, how about all of R itself? You could think of as a giant interval, right? Minus infinity to infinity. Are those equivalent to any of the ones that we've already talked about, or are they their own things? These and more mysteries we will discuss next time. All right. See you then. Let me know if you have homework questions.